Okay, let's get started. It is my pleasure, great pleasure, in fact, to introduce one of our colleague, Professor Feng Wang. Feng got his bachelor degree from Fudan University. And afterwards, he went to Columbia University and got his PhD there. So we were lucky enough to attract him as a Miller Fellow afterwards. And after Miller Fellow, he joined the faculty here in 2007, right? Yeah. So Feng is a leading expert in optical spectroscopy of the low-dimensional material. For example, his study of carbon nanotubes and graphene really advanced the exciton, which is a bound state of electron-hole physics in condensed matter. Recently, Feng has been at the forefront of optical spectroscopy of two-dimensional material, such as Moray systems. Feng's research is really characterized by the advanced laser technology and extremely insightful, physical ideas. So Feng has many awards. Among them, he has the 2024 Frank Isaacson Prize for the physical property of solid. So please join me in welcoming Feng.
Oh, I would like to thank Donghai for the introduction. It's really a great pleasure to give a talk to the home audience. Today, I will tell you some of our recent efforts trying to explore Exciton Bose-Einstein condensation using atomically thin heterostructures. This semester, I'm teaching 5B again, and to motivate the students, I told them, if you combine electromagnetism, that means Coulomb interaction, and quantum mechanics, you can explain most of the physics that we experience in daily life, and almost all chemistry and biology. Because if you combine negative electrons with positive protons, or they can form atoms, then you can add charge to form ions. And build on the atoms and ions, you can get molecules, solids, and even biological systems. So the key is to have Coulomb interaction where you actually have both attractive and repulsive interactions that they can kind of have interesting interplays. So if we look at what condensed matter physics mostly does, we are interested in different quantum phases of electrons, let's say at the ground state. And or they can be extremely rich. The electrons, when you put them in periodical lattice, add quantum effects and add electron-electron repulsive interaction, or you can get not only metals and semiconductors, you can also get superconductors, magnetism, and different topological phases. And this very rich behavior comes mostly, repulsive electron-electron interaction plays a very important role. So one can help to wonder, what if you can have electron-electron repulsive interaction, but also attractive interaction? So what if you combine like attractive and repulsive interactions for electron system? What kind of new phase it might lead to? This question is actually not that new. For people who do optical spectroscopy or study excited states, to create attractive interaction is pretty straightforward. So what you can do is you can shine light on a semiconductor. It can kick an electron from valence band to a conduction band. So now you have electron in the conduction band. The vacant electron in the valence band basically is described by our positive charged holes. So now you actually have an electron system that has both positive charge and negative charge, and they can have attractive Coulomb interaction. And the effect of this Coulomb interaction can be very important, and is a kind of favorite topic in optical spectroscopists. For example, if you have positive and negative charge, they can bond together and form a system similar to hydrogen atom. Like you will basically have a bound electron hole known as excitons. Or this exciton can grab an additional charge, just like ions. They can form something known as trions. These excitons can also form a pair, like form an exciton molecule, or also known as bi-excitons. And further, if you have many of them, they can also have a two-component plasma, electron hole plasma. So people have been wondering, if you have these new type of many particle quasiparticles, so what type of behavior they can lead to? Take the exciton as an example. You see it has two charges. That means if electron is a fermion, two electron or electron hole combined together, it actually becomes a boson. So it's a bosonic particle, and if you cool it down to low enough temperature, or very likely they will form a Bose-Einstein condensate of excitons. And this topic has been actually actively studied in the 60s, more than 60 years ago. And there are several influential papers talking about how you can realize a Bose-Einstein condensate potentially at rather high temperature coming from the excitons. Because this exciton has a mass that's much, much smaller than atoms. So they actually, Bose-Einstein condensate temperature, the quantum effect is much stronger. And the BEC can be at rather high temperature. That, of course, motivated a lot of experimentalists try to look for it. Even after many decades of active searching, it turns out this experimental search has not been successful. And the main reason is in a conventional semiconductor, when we create these excitons, we need to shine light. And these excitons are excited states. They don't live forever. In fact, they tend to live only in, say, nanosecond time scale or even shorter. So the result is very hard for them to thermalize and relax to a ground state before they recombine, or during the recombine generate even more heat. So that actually becomes mission impossible. So then researchers are wondering, can we overcome this problem? Is it possible to engineer an exciton that live forever, or at least live for a very long time, that everything can be fully equilibrized? And that led to this idea of electron hole bilayers. So the idea is, not having electron and hole too close to each other. You put electrons in one layer and hole in another layer, and use a very large kind of a tunneling barrier to prevent the electron and hole to recombine. In this case, this electron hole then will have attractive interaction, and they live very long, and we can explore their ground state property. Or in this kind of system, of course, one of the key parameters is the separation between these two layers. You want it to be kind of large enough so that the electron and hole tunneling are really suppressed, so they live for a very long time. But at the same time, you want it to be very small, because you want the electron hole interaction remains very strong, and it can compete effectively with the repulsive Coulomb interactions. So the first experimental trial of this bilayer system starts when we have gallium arsenide quantum Waals structures, where you can grow these heterostructures pretty well controlled way. However, due to the material limitation, the smallest d that we can use in this conventional semiconductor heterostructure, or to prevent the electron hole recombination, needs to be larger than 10 nanometers. Although this sounds pretty small distance, but compared with like atomic thickness, is already pretty large. And then combined with relatively large dielectric constant of the gallium arsenide, at the end, the attractive Coulomb interactions of the electron hole remains rather small. So at a zero magnetic field, you can barely see this exciton physics. So in order to see things interesting, people tried to go to quantum Hall regime at very high magnetic field, and many interesting things are indeed observed. So what we want to ask is it possible to actually stabilize a strongly interacting excitons at a zero magnetic field? Basically a conventional exciton. And in order to do that, it's very important to control the distance at really atomic precision. Depending on what's the optimal condition, you might want just one atom layer or two atom layer, or maybe a few atom layers to optimize the system. And to address this challenge, we'll make use of this now kind of emerging material family known as van der Waals heterostructures, or basically layered materials with van der Waals bonding. Or everyone is familiar with writing with pencil. So that's one of the most important layered material, which is basically graphite. When you write down on your paper, you are exfoliating these thin layers of graphite because they have very strong in-plane kind of covalent bond, but very weak kind of layer van der Waals bonding. So as a result, you can exfoliate these layers very easily, even during you writing with a pencil. So the question is, can we control this exfoliation accurately enough that we can get a single atomic layer of this graphite? That turns out to be doable. All you need is a Scotch tape and a lot of patience. So you use a Scotch tape to basically kind of continuously exfoliate this graphite. And after some time, it's actually possible to get down to a single layer of graphene. Very soon after the observation of graphene, people realized there's really a host of materials family that you can play with. They are layered van der Waals heterostructure, and you can use Scotch tape to exfoliate them down to a monolayer or few layer limit. They can be insulators like boron nitride. They can be semiconductors like some of the transition metal dichalcogenide. They can also be superconductors, magnet, and or many other different phases. So the most exciting thing is once you isolated these atomic thin layers, you can stack them up again, or you build up things with Legos. So now you have your different Lego pieces. Depending on what you want to study, you can combine different pieces to make different type of heterostructures. Initially, when people draw this, a lot of people think this is kind of just a wishful thinking cartoon. But researchers did try. So they actually just use a relatively simple plastic stamp. After you exfoliate the monolayer or few layers, they can pick up a piece of boron nitride, pick up another piece of graphene, and pick up another boron nitride. So you can really stack them like atomic Lego. And the most important thing is these Legos are of very high quality. So if you do a TEM imaging of this heterostructure from the side view, or you can see these individual layers of boron nitride, graphene, and boron nitride, they basically form perfect interfaces. So they actually form atomically clean heterostructure, which is extremely important. If you want to study fundamental behavior of electrons, you want the system to be very well defined and very clean. So this shows that this is indeed possible, and it led to a boom of a lot of researchers trying or combination of different heterostructures to explore different physics, or like Maury heterostructures and so on and so forth. But today, I will narrow the heterostructure that we are going to play with. We focus on the electron-hole bilayer. That means we'll need two semiconductor layers that host the electron holes and insulating layer to kind of isolate them. So we're mostly using this MOSE2 and the WSE2 because they have a relatively small band gap. They are relatively easy to exfoliate and kind of work with. And the optical spectroscopy of them are also easy. So that's how we kind of choose these two semiconductors. And we use a thin boron nitride as the dielectric barrier. So this boron nitride we can control with single layer precision. So we can decide whether we want a 5-layer dielectric or 6-layer dielectric, depending on the device configuration that we want. And then we will kind of dope electrons and holes in the semiconducting layer, which the electron hole recombination will be suppressed by the boron nitride, and they can live for very long. Okay, so what I want to tell you today is, or if we can make these electron-hole bilayers, first I need to give you some background, like, or how do we actually know what's going on in them? So I'll talk about how we can use optical spectroscopy to read out local electron and hole densities as well as their spins. Then I will tell you how we can kind of use the heterostructure to build these excitons, trions, and biexitons, these composite particles, and demonstrate they indeed exist. Last, I will talk about, or once we have these kind of a composite at their ground state, what kind of quantum phase they can lead to. And I will just focus on excitons. It turns out that these excitons will form an interesting quantum phase known as a two-component Bose-Einstein condensate. Okay, so let me start with the first topic. I here again show a kind of illustration of a typical structure. The key component is this MOSE2 and WSE2, two semiconductor layers that can host the electrons and holes. They have a boron nitride dielectric in between. At the same time, we also have a top and bottom gate, so this dual gate. And each of these layers can be controlled electrically. So this electrical knob is extremely important because they allow us to in situ tune the effective band structure and the doping, and then explore different phase diagram. So let me show you how the different voltage actually modify the behavior of the system. And they are kind of key to understand what I will talk about later. So first, if we, without applying any gate voltage, we have this WSE2 is a semiconductor, MOSE2 is another semiconductor. They have this so-called type 2 band alignment. In that, conduction band minimum is in the MOSE2 layer. Valence band maximum is in the WSE2 layer. But still, there is a finite band gap. As a result, at zero temperature, zero voltage, it is a well-behaved semiconductor with zero doping. However, we can introduce simultaneous electron-hole doping with two ways. One of them is to apply a bias voltage between the MOSE2 and WSE2 layer. So this bias voltage will shift the Fermi energy of electron relative to the hole. So what you can imagine, if you shift the Fermi energy up and shift this Fermi energy down, then you can have electron doping and hole doping at the same time. So you always get equal doping in this case. The other way is actually applying a vertical electrical field. So you can apply an anti-symmetric gate voltage between top and bottom gate, generate an electrical field. So because top and bottom layer are at a different position, the effective field will shift their energy relative to each other. So what you can see is initially they have this band alignment. If you shift the energy of this one down enough, then the conduction band and the valence band will start to overlap. So even if you have the same Fermi energy, you actually now have simultaneously electron and hole doping. So basically, these two knobs, bias voltage and vertical field, do effectively the same thing, that they allow you to introduce like equal amount of electron and hole doping. So in reality, the maximum voltage you can apply is limited by the breakdown behavior of the dielectric. So usually we need to combine these two knobs together to realize electron-hole doping in the real system. So now, when you have equal electron-hole doping, if you want to actually change the electron-hole balance, what you can do is use a symmetric gate voltage. So if you apply, say, positive gate voltage on this top and bottom gate, they will attract electrons. So it will be able to inject basically additional electron. Or if you apply negative gate voltage, you can introduce additional holes. So that basically allows you to kind of modify the net charge distribution. So here I show an illustration on how many kind of layers you need in order to form such a stack. Even for a simple, or at least conceptually simple bilayer device, you actually need more than 10 van der Waals stacks to make it happen. So it's actually rather heroic devices for any of the things that I talk about. I would say if I'm a graduate student, I doubt I myself can do it. Okay, so once you have this kind of a heterostructure, and if you dope electron hole to the system, how do you know what's happening? So we can make use of the optical spectroscopy, which has already been well established for these monolayer semiconductors. It was well known. They have very strong Coulomb interactions, so they form tightly bound kind of optical excitons inside the layer. So if I look at the optical spectroscopy, or which is reflection as a function of wavelengths in the vertical axis and the gate voltage on the horizontal axis, over here the system is undoped. So you have a regular semiconductor, and you can see there's a very strong response here that actually corresponds to an exciton transition in this monolayer. So this is an optically excited intralayer exciton, so electron hole sitting in the same layer. And then what we can see is when you apply gate voltage, which will attract a hole in the layer. So you basically have a hole doping, just like a field effect transistor. And you can see the spectrum start to change. The exciton resonance become weaker and shifted, and a new peak appears. So that actually corresponds to a trion. Basically, the exciton is bound to another hole, and that's basically the inside a monolayer itself. So this is known as the intralayer trion. And we can all convert the gate voltage into the carrier doping by just using capacitance model. So then what you can see is that, you actually have a changing of the optical spectrum at a different carrier density, and there's a one-to-one mapping between them. So after this calibration, what it allows us is to perform an optical spectroscopy and then directly read out what is the hole doping in the system. So we have a kind of a remote way to know how much holes we have in the layer. And the same can be done for the electrons. So here I show the spectrum, again, reflectivity as a function of wavelengths, and the electron density. What you can see is the exciton signal change and a new trion appear once you have kind of finite electron densities. So again, with optical spectroscopy, I can read out how many electrons I have. So this is for isolated layers. Now, if we have two layers together and we can do an optical spectroscopy, what you see is the two layers are two different semiconductors. They have different band structure, and then they have different exciton resonances. As a result, we can actually read out them separately. So this peak is WSE2 exciton resonance, and this peak is MOSE2 exciton resonances. And when we change gate voltage, we can see here, hole is doped in the WSE2. Here, electron is doped in the MOSE2 because you have the kind of electron side trion. And in the middle, what you can see, the electron side has a trion, that means it's electron doped. And the hole side has a trion, that means the hole is doped. So we can actually directly find the electron and hole are now both injected in the system. And if we quantitatively measure the spectrum and compare with our calibration, we can determine exactly how many electrons we have and how many holes we have. In addition to optically read out the electron hole density, we can also read out the spin density. It turns out this monolayer transition metal dichalcogenide has some interesting optical selection rules. So first, the conduction and the valence band minimum are not at the center of the Brillouin zone. Instead, is at the vertex of the Brillouin zone. And there are two inequivalent pairs. So they are basically the time reversal pair. One is at k value, and one is at k prime value. And due to spin orbital interaction, the spin and the value are locked. So what I mean is, if you look at the highest energy of the valence band, the spin down electron is living at the k prime value, and the spin up electron is living at the k value. So once you know where the value is, you actually know what type of spin the electron or hole have. And furthermore, there is an interesting optical selection rule for these exciton transitions. If you use sigma plus, let's say, one circular polarized light, it can excite only k prime value. And use opposite circular polarized light, you will excite only the k value. So this happens when you have like a pristine semiconductor. You have basically optical selection rule for excitons. Turns out we can make use of this then to read out the spin of kind of a doped charge. So let's see what happens in this case. So let's imagine we have our WSE2 layer, and we dope some hole in the system. And the hole can be either spin up, then it will live at the K value, or it can be spin down, it will live at the K prime value. So now I send in a circular polarized light with sigma plus polarization and measure how the optical transition look like. So with sigma plus, we will only be able to excite electron-hole pair in the K prime value. So what you can see, this optically excited exciton will interact with the original hole in very different way in these two parts. If you look at this one, all the two holes have opposite spin in different value, they can form a singlet pair. So as a result, this will allow the whole three particle system together form a bound trion state and give you a trion resonance. On the other hand, when our optically excited exciton is in the K prime value and the original hole is at the K prime value, this hole have the same spin. They actually have Pauli repulsion, and they cannot form like a bound trion state. So as a result, if you are sending the circular polarized light and see the trion signal, you can directly know it's coming from a hole, the spin up hole. So indeed, we can actually use this to measure spin up hole density. So at the zero magnetic field, let's say we dope the system, half of the hole are spin up and half of the hole are spin down. When you apply a magnetic field, what you can see with positive magnetic field, or more spin will be up, then this trion signal intensity increase. And when you apply negative magnetic field, or the kind of spin up, spin are depleted, and you see reduced signal. So basically with this optical circular polarization, we can read out the spin density directly for both electrons and holes. Okay, so those are kind of the background. So those are the tools that we are going to use to probe what's going on in the electron-hole system. Next, I will show you that how do we basically engineer these excitons and trions and biexcitons, and in particular demonstrate that they really exist. It's not something in our imagination. So again, we start with this bilayer system. We can inject electron and hole here. So the experimental condition is we will fix the vertical electric field that allow us to basically make the initial band gap, effective band gap of the two layers to be relatively small. And then we will use these two as our tuning knobs. One is the bias voltage that allow us to control how many electron hole we dope in the system. And then use this gate voltage then to modify the additional net charge that we'll have. And here I basically plot out how the electron density and hole density that we can read out optically as a function of these two control knobs. So what you can see is when the bias voltage is relatively small over here, you can either have hole doped by applying a large, this gate voltage, or electron doped. So you cannot have and in the middle part, nothing is doped. So you cannot have electron and hole doping at the same time. But when you apply a large enough bias voltage, then you basically shrink the effective band gap to 0. You basically find you have both electron hole doping in this region and the electron doping in that region. So we know that all qualitative things are looking pretty good. So now what we want to know is, when we have both electron and hole doping, do they form excitons? Or do they just behave still like just free electrons and holes moving around? So it turns out once we have the density as a function of gate voltage, we can determine a thermodynamic quantity known as compressibility. So that is, how does the density change when you apply a gate voltage? So what we know is if you have freely moving electrons and holes in a field effect transistor, so when you apply a gate voltage, you can increase the electron or hole density. This is known as a compressible electron and hole fluid. So here, basically, we are just plotting out the net charge, which is electron density minus hole density. So if you add any net charge, this will be non-zero as a function, derivative against the gate voltage, which allow you to change the net charge density. And it has an interesting behavior here. The red part means it's compressible. That means you can either add single or individual electrons or add individual holes. And then the white region are incompressible. That means you cannot add electrons or holes by themselves. So this white region, the bottom part of the white region is actually easy to understand. So that is where you have a finite band gap in a semiconductor. So if you have a finite band gap, it actually has some energy cost to add electrons and holes. So it's naturally that you have a finite region that's not compressible. The very unusual region is this tip of the triangle. Here, what you can see is we already have electron here and a hole and the electrons over here. So that means we actually have already doped the electron already. But why is it still incompressible? So it turns out that this is a hallmark of the so-called exciton insulator. What happens is basically we have doped electrons and a hole here, but they are not independent free-moving charges. Instead, they all pair up into excitons. So you can add exciton in the system, but you cannot add either electron or hole in the system. So what happens is like, if you look at a single particle band structure, there is still a finite gap. So it's not possible to add the electron or hole with zero energy penalty. So you kind of need to add some additional bias voltage in order to add the electrons. However, if you add the electron hole together, they actually are bound. They have a finite binding energy. So they are happy, and they can go together in the system. So that basically means this triangle region is basically well-behaved exciton system. By looking at this, we can also estimate exciton binding energy. So let's say if I just increase, right above this kind of dashed curve line, we can see that there is about 30 milliwatt range that I cannot dope electron hole. That actually corresponds to an exciton binding energy about 30 milli-electron volts. Or if you think about the room temperature thermal energy is 25 millieV, this is actually a respectable exciton binding energy. And further, what we can see is the width basically becomes narrower when we increase the exciton density. So that actually tells us this or many-body exciton interaction actually will renormalize the exciton binding energy up to a critical density. What you can see is beyond that critical density, it actually becomes now free-moving electron hole plasma. The exciton binding energy becomes zero, and that's known as like exciton Mott transition. Okay, so now we know that we indeed have pretty tightly bound exciton in the system. How about trions? So in that case, we will need an exciton to capture an additional electron or capture an additional hole. So in order to form the trion, now it's really important to make this distance very small. The reason is if you increase the distance, the repulsive interaction between the same charge remains the same, but the attractive interaction becomes weaker. So very quickly, the trion will never be stable anymore. So the theory predicts, you need only you need to control things within a few nanometers. So we kind of push the limit to see the strongest effect. We only use 2 or 3 layers of HBN in this case. In that case, now we can again look at the spectrum as a function of our gate voltage. So in the middle vertical line, this is where the kind of electron and hole density remains 1 by 1. So this is the exciton regime. We can see we have electron and hole doping. And then when we change the gate voltage to add excess holes or add excess electrons, you can see something actually happens over here that corresponds to electron and hole densities 1 to 2. So what happens is basically the original trion peak actually disappears and a new peak appears. Something also happened at the electron 2 to 1 ratio, but it's kind of weaker. So let's focus on the hole side, 2 hole, 1 electron. So why does this happen? First I want to show this is actually a signature of the trion by looking at this basically trion, this feature across the whole phase diagram. What you can see is the this feature is very well correlated with 1 to 2 doping line. So that means it's not or just a coincidence at some kind of a density, like across the whole trion density, actually, 1 to 2 ratio, this spectral feature is there. But to further convince us this is a real trion, we can look at their spin behavior. So what happens is, first, let's see what happens when you have just a free holes. Or the free hole basically will have a paramagnetic spin. So if you apply magnetic field, the spin polarization will change, and then spin up density of the hole will vary continuously. And this is what I talked about before. So by using circular polarization, you can see basically the all spin, there are more upspin with positive magnetic field, and then less upspin with negative magnetic field. So now let's look at the new peak and see how does it change with magnetic field. So what you can see is, is actually at low field region, it's symmetric to left positive and negative field. And close to 0, basically, it's not changing much. So that's a hallmark of the trion, because a trion will require, again, the 2 holes actually form a spin singlet. And if you have a spin singlet, of course, it doesn't respond to magnetic field. You cannot change the overall spin of the holes. So it basically remains more or less constant until the magnetic field is large enough. So what happens is when magnetic field is very large, or this bound trion cannot benefit from it because it has spin singlet. It does not have Zeeman splitting. But or if you have separated exciton and hole, then they are paramagnetic spin. They can lower their energy through exchange energy. And sooner or later, they have lower energy than trion. Then you dissociate the trion. And then basically, that's when the trion disappears. So based on the Zeeman energy, we can actually estimate that this trion binding energy is relatively small. It's only at 1 to 2 millieV level. OK, so we check the box of trion. How about biexcitons? So if we have still 2 layers, it turns out that these 2 excitons cannot form molecules because they both have an electrical dipole pointing maybe downwards. They have the same dipole. Then they repel each other, and they cannot form bound state. However, we can make use of this kind of a flexibility of van der Waals heterostructure to make a 3-layer system. Now, if you introduce electron-hole and the electron layer, then in this case, you can form one type of exciton with kind of a dipole pointing down, and then the other exciton with dipole pointing up. So now, if you have opposite dipole, they will have attractive interaction, and they will be happily to form this kind of exciton molecular state. And or indeed, we can fabricate these tri-layer devices. Now you can see there are even more control voltages and become really complicated if you look at the global phase diagram. So we'll narrow our attention just to the charge neutral region. So basically, we'll only use these 2 knobs, the bias voltage and then asymmetric voltage between the top and bottom layer. In this case, we will always inject the equal number of electron and holes. So they basically, so that is all. Net charge is always 0, but we can control whether there are more kind of one type of exciton versus the other type of exciton. So this is a phase diagram that we expect. So if you increase the bias voltage, you just add more and more excitons in the system. And when you vary this vertical field, you will prefer one type of dipole versus the other type of dipole. So you can change the balance between these 2 dipolar excitons. And again, to know what's going on, we read out the electron density of the top layer and the middle layer and the bottom layer. So here you can see that the kind of top layer is doped here in this range, and the bottom layer is doped in this range, and the middle hole layer is doped in this range. It's actually matched with the expected phase diagram. But now to know that we indeed form the bound biexciton state, or we can again convert the density to the compressibility of the excitons. So let's say if you have kind of independent excitons, they are not bound, Then if you apply a vertical electric field, you can continuously switch one type of dipole to the other dipole with no kind of energy band gap. However, if they form a finite kind of or if they are bound into these biextons, they will have a finite gap to polarize one into the other. So, or experimentally, we can kind of obtain this compressibility of moving one charge from the bottom layer to the top layer versus this vertical field. And what you can see, there is an incompressible region kind of in the middle when the excitons, the two type of exciton have exactly the same density. They all form basically bound biexton. Okay, so I hope I've convinced you that with this system, we can engineer different composite. So the most interesting question is then, what kind of quantum phase they can form? Let's focus on the excitons. Okay, as I mentioned, the exciton is a boson. When they are at low enough temperature, they should become a quantum degenerate bosons. But how do we know? So we kind of need to have some kind of experimental ways to grab on this behavior. So one proposal by theory is actually measuring the so-called exciton superfluidity. So the idea is the exciton is a global condensate, then the exciton can transport with no dissipation. And if you then convert it into electron-hole movement, let's imagine if the exciton is moving along that direction, then the positive charge moves that direction, and negative charge, the current is, positive current is that direction, and the electron move that direction actually means electrical current move that direction. So as a result, if you can do a counterflow measurement where like current flow this way and that way, and then measure their like resistance of this counterflow, you should see zero counterflow resistance. However, this measurement is challenging for us because it requires very good electrical contact to TMD. So we are trying, but not there yet. So what else can we do? Or if you have a condensate of like a quantum degenerate gas, they should also have very important effect on the spin behavior. So let's take a look at how the exciton spin now will behave a little bit more carefully. At low energy, there are actually 4 different exciton flavors that's possible because all electron and hole can be at either spin up or spin down. So there are 4 different pairings. And because spin and valley are locked, they also correspond to specific valley behavior. So you have all these so-called intra-valley excitons, where the electron and hole are both in the same valley, K or K prime. Or you can have these inter-valley excitons. So, or if you have classical exciton gas, where the excitons don't interact and talk with each other, and you just look at the classical thermodynamics, it turns out that the spin of electron and hole, spin of hole are not affected by anything else. They basically behave as a 2-level system at a finite temperature, and they will be just a paramagnetic spin response. So we know they will have a tangent type of shape polarization as a function of magnetic field. And because the electron and hole has a different effective G factors, so they will have different slope, and they will be saturated at a different magnetic field. Now, let's see what will happen in the quantum regime. So if you have exciton condensate, and if you assume that they have minimum interactions, it turns out, so let's say if even initially these 4 states are degenerate, apply a very small magnetic field will break the degeneracy because this state will have a large G factor than these intra-valley excitons. And or this one will have low energy, and this one will have a high energy. So basically, this one will have slightly lower energy, even at minimum magnetic field, compared with the other 3 states. And the fascinating thing about boson condensate is even a tiny, tiny energy difference will lead all the excitons to condensate in that specific state. So as a result, an infinitely small magnetic field will completely polarize the exciton, and then it will form basically a 1-component exciton condensate. And it will be effectively ferromagnetic. A smallest magnetic field will basically polarize it. And then electron and hole also get polarized at the same time. Things could also be a little bit complicated if you introduce the interactions between the excitons. If you have exchange interaction, it's actually possible to stabilize a two-component exciton condensate where it's kind of forced to have, let's say, both intervalley excitons or both intravalley excitons. So in this case, the spin susceptibility will be a little bit complicated. But nevertheless, one thing we expect is electron and hole will have a strongly correlated behavior because, or if you have this type of exciton, or they will have the same electron and the hole corresponding value or spin densities. Okay, so let's see what the experiments say. So here we show the electron susceptibility as a function of exciton density and magnetic field. So this is in a kind of a fine magnetic field range, and this is a broader magnetic field range. So it's obvious it's not a ferromagnet. It's also not a paramagnet. Instead, it has pretty complicated behavior. And if you look at it, it's kind of striking. There are maybe easily see there are three different phases. We call 2A, 2B, and 1. So in the 2A phase, you can see the color actually blue and red has opposite signs. So basically, effective susceptibility actually changes sign for the electrons, but it's reduced for holes. And then in 2B phase, you have large susceptibility. And in 1 phase, it's actually they are fully polarized, and you don't have any polarizability anymore. So the other thing to notice is this 2A phase actually expand with exciton density until the multi-transition where the exciton is gone. So that means this is a really exciton-exciton interaction-driven phase. And also, what you can see is the phase boundary for electrons and holes are perfectly matched. So they have very strongly correlated electron and hole behavior. So this tells us these are really exciton behaviors, not separated electron and hole having some strange physics. And also, the exciton-exciton interactions are very important. So we can actually understand this rather complicated behavior using a relatively simple interacting boson model. So this is basically the order Hamiltonian. So you just have the behavior of individual exciton species and plus an interaction mediated by exchange between kind of or like intravalley excitons or intervalley excitons. So let's see what the single particle kind of energy look like and how does the interaction modify the behavior. So again, there are 4 different exciton species. When you look more carefully, the intravalley excitons are kind of linked by time reversal symmetry, so they must be degenerate. And this must also be degenerate by symmetry. But between these two, they're actually not symmetry protected. So it's possible to have a small energy difference between these two type excitons. And let's assume there's a finite energy separation delta within the microelectron volt level. And then when you apply magnetic field, of course, there are Zeeman splittings. Intravalley excitons have a smaller Zeeman splitting because the hole and the electron contribution cancel each other. So you have only their difference. And the intervalley excitons have larger Zeeman splitting because the G factor from electron hole add up together. So now let's look at what does the interaction do. So if the exchange interaction is smaller than 0, it will favor a ferromagnetic state. So basically, you have a single component condensate. On the other hand, if you have Gx larger than 0, so you actually then want to have finite N1 and N2. So that actually favors a 2-component condensate. So the situation is, Hartree-Fock calculation tells us in our parameter range, Gx is smaller than 0. So it should be a single component condensate. Of course, that doesn't match with our experiment. But Hartree-Fock can be wrong. So we'll just phenomenologically choose a positive Gx. So that basically say we have 2-component condensate. And then see when you combine these with the single particle band structure, what do we expect? OK, so when you combine that, so you have 3 different types of possible condensate, like intravalley 2-component, intervalley 2-component, or a single component one. At zero magnetic field, they have different energies. But then when you apply magnetic field, they have different slope because they have different G factors. So let's walk through this a little bit more. So at the zero magnetic field, these inter-valley excitons condensate are favored. So you have equal distribution of K and K prime valley excitons. When you apply a finite magnetic field, or this energy of these two becomes slightly different. So the density of these also becomes slightly different. But because the G factor is equal to whole contribution minus the electron contribution, so the net G factor is small. So as a result, the susceptibility will be weak. So you have very kind of a small slope. But also what you can see is it will listen to what whole wants to do. So it will go with basically a spin polarization with the whole direction. But it's actually opposite to what the electron wants to do. So as a result, electron actually spin energy will increase, but the total exciton energy will decrease. So what you can see is something like this, a small slope along the whole polarization direction, but then electron polarization direction is actually opposite to what it naturally wants to do. But then up to a critical magnetic field, or the inter-valley exciton takes over because it has a larger G factor. It can benefit from the exchange, the Zeeman splitting better, and then it will finally get a crossover and have lower energy. So you have a first order phase transition into this inter-valley exciton condensate. And then they will have a larger G factor. So basically you have a larger slope until everything gets fully polarized. With this relatively simple kind of interacting boson model, there are only two unknown parameters that we need to use as a fitting parameter. One is the single particle energy separation. One is the effective G factor. Then the theory actually can predict the rather complex experimental observation quite well. So there are three different phases. And at finite magnetic field, you can basically have first order phase transition from type 2A to type 2B. And then the electron side and hole side are completely kind of matched with each other. And also the phase region basically expand when you have higher density because the exchange interaction becomes stronger. Now we think we have these two component exciton condensate. We can also ask, how does it change with temperature? What's the critical temperature of the condensate? So we can measure the spin susceptibility as a function or with small magnetic field, but also like with different temperature. And then we can do vertical line cuts for the 2A region and the 2B region. So what you can see is, in the 2A region, the susceptibility is strongly suppressed. The 2B region, the susceptibility is strongly enhanced. And there's a TC around 1.5 Kelvin, and then they collapse into basically paramagnetic behavior. So this is kind of or somewhat consistent with the basically the condensate basically disappear at finite temperature. This is at a fixed density. We can also look at the overall phase diagram and see how does it change with densities. And we see the exciton Bs actually form a dome-like structure. At a small magnetic field, small density, it is constrained by this blue dashed line. So it turns out this blue dashed line is a theoretical prediction for the BKT transition. So basically, but when you go to a higher density, of course, it deviates from the BKT behavior and up to a certain density, which is a critical density of the exciton mod transition. So where the total exciton gap goes to 0, and of course, exciton condensate also disappears. Okay, with that, I come to my conclusion. I hope I have shown you this atomically thin semiconductors actually establish a rather powerful platform for us to study this electron-hole bilayer, where we have both repulsive and attractive Coulomb interactions. We can have excitons, trions, and biexcitons. And then excitons can form a two-component Bose-Einstein condensate. It also opens up many questions. First, we still don't know why it formed two-component exciton condensate. Simple theory actually says otherwise. But beyond that, we can ask, what about BCS-BEC crossover kind of close to the multi-transitions, or if we use different 2D material, or what's the ultimate limit of TC? Is it possible to get a TC much higher, tens of Kelvin, or maybe even room temperature? And then whether we can improve the contact to really see exciton superfluid flow, or maybe even Josephson junction, or like exciton circuit. Beyond excitons, we can also ask, what about trions? Can they form Wigner crystals? By excitons, they might also form a condensate of their own. And when you have mixtures, of course, they can also give rise to interesting behavior. With that, I would like to thank people who really did the work. Most of the work, actually all the work, are spearheaded by Rui Shi, which is kind of an extremely talented graduate student. He works very closely with Chiza from Professor Cromie's group. We collaborate very closely. And he have collaboration, also help from Jiahui. And there are quite a few students and postdocs in the group also helped in the project. And we have theory support from Zelatel with Tianle and Zhihuan. And also theory collaboration with Liang Fu from MIT and Alan McDonald in UT Austin, and the boron nitride comes from the NIMS group. And thank you for your attention.
Any questions?
I guess so. Since you're sort of like your 2A phase for looking at the magnetic susceptibility, that seems to be a secular response to say that the energy is quadratic in the field. So, or I guess my question is, how do you distinguish spin susceptibility from orbital susceptibility? Or are you just sort of measuring the overall susceptibility?
So actually, this circular polarization measurement directly determine whether it's at K or K prime value. And that's directly associated with spin. So these are purely measurement of spins. If you, let's say, have or change the orbital, but it remains at K value, it actually will have minimum effect in this measurement. Okay, so we change magnetic field. We can measure either charge density or spin density. So these are all spin susceptibility. We are actually making use circular polarized light to directly determine what's the spin density in the system, not the charge density. Yeah.
Is it possible for holes to have spins because they're cavities, they're not, they're vacancies, right? So how is it?
Oh, so basically holes are missing electrons. So if electron initially have a kind of or certain magnetic dipole, let's say, then missing the electron will have effectively the opposite magnetic dipole. So a hole can have both spin and magnetic dipoles.
Yes. So everything you mentioned thought about the electronic degrees of freedom, but of course there is a lattice there also. I wondered to what extent electron-photon coupling might explain the renormalization of the exchange interaction or other effective interaction.
We think the electron-phonon interaction is relatively weak, like at this low energy level. But yeah, it's not obvious for how the phonon play a role. So it's possible. We should check. But it's not obvious why it will be important here.
Yes.
This is really, really beautiful. I'm very impressed. Now that we have the DEC, can you also create some topological the configurations like vortices and stuff?
Possibly, we are thinking. So of course, it doesn't couple to magnetic field as easily because it's a charge-neutral system. But the thing is, we can use gate basically to create a local defect. So if you do have a local defect, and then, I mean, this may be also more similar to like a helium case. You cannot make a vortex with magnetic field, but you can rotate things around to drive a current flow around a center. So maybe we can use RF waves, for example. I mean, the good thing is the exciton does have a finite electrical dipole. So we can actually use certain kind of electric field to manipulate the flow in some way. Yeah, we are thinking how to implement it. Yeah, it's non-trivial.
Is it possible to look at the radiation field to look at phase coherent effects emerging in your exciton condensate?
Yeah, it's a good question. So for this case, we really want to have the exciton live very, very long. And then the electron hole tunneling is strongly suppressed. Then they don't radiate much. And also, if we see their radiation, it turns out, so maybe the defect is still important. We find that even with the very small leak current that we do see, most of them are still going through non-radiative channels rather than radiative channels. So like, yeah, we are hoping that we can also see radiation. We are maybe pushing the BN to be thinner so the tunneling can be stronger. But it seems defect, maybe the non-ideal material like plug everything, is still prevent this to be easily observable. But yeah, we're actually wondering what's ultimately limiting that.
Yes. If you change the magnetic field, would that cause a rotational current that could affect the spins? The scaling of the
Yeah, if you have pure electrons, magnetic field will form the Landau level and drive things around. But if they actually form tightly bound excitons, the exciton is a charge neutral thing. They actually don't form this current loop easily. Like,
so would increasing the magnetic field cause a current that would be interesting?
yeah, it can change the internal actually binding energy of the exciton slightly, but overall, yeah, it's very different from pure charge. Like, so its main effect is on the spin part.
Yes.
Well, in the old days, we were talking about 60 years ago, a lot of people have tried to look at excitons in 3D systems and to try to observe Bose-Einstein condensation. So they were looking at more simple excitons where magnetic field is not necessary, and the only non-return is usually the density by bringing up the laser power and also change the temperature. So in principle, you are looking at, hopefully see a phase diagram there. And the signature we used to look at is just looking at the emission, because you expect that in the simplest model of non-interacting bosons, then when all the excitons condense into the K0 state as predicted by Einstein, then you expect to see spectral narrowing. And of course, most of the time, we did not see that signature. So I was wondering whether in your measurement, have you looked at the spectroscopic signature of condensation?
Yeah, that's basically also the ALPS question. Like we tried, but it's not there because with this thick BN, like the electron hole basically wave function are largely have no overlap. So they actually doesn't really recombine and emit a photon easily. But you can say maybe, or there will be some kind of a tunneling probability, so they can still recombine. But what we found is like in or non-ideal semiconductors, the non-radiative channel completely dominate. So the kind of a radiative kind of coherent channel, we cannot see anything. So maybe with improved sample quality, there is a hope, but we have to see.
Another possibility is that you have a good way to vary the insulator separating the electron hole pair. You can tune that.
Yeah, we do that. So we can control that layer by layer. We can have one layer of BN.
The minimal distance is not zero. If you can really go down to close to zero, then you will be able to enhance the exciton.
Yeah, but then the problem is then electron hole lifetime becomes limited. Let's say if we don't put any BN in between the two semiconductors, so first they talk too much. And the other one is actually then the electron hole start to recombine and you cannot kind of create this.
3D
Yeah, you kind of need to work a fine rope that you can make them long-lived and you can study them in ground state, but at the same time, like the interaction is strong.
And this, I guess the question is, if you have these in this two-component phase where you have this 1, 1, 0, 0 condensate, there's this relative phase between the two ones. Does that have a signature in your experiment? Like, is the relative phase of population in K prime?
No, it will not have a signature that we can see right now. Like,
is it locked, do you think? Like, with defects that mix K and K prime, would that lock that?
yeah, that's an interesting question. If you have some Josephson coupling type of thing, they might lock. But so in our simple model, they basically are not locked. It's like they favor you have both components, but then the phase is not locked in the simple model. But I don't know if you look at the higher order kind of corrections, whether there will be some like terms that try to lock them.
When you draw this DKT drawing, does that account for that additional?
No, this is assuming they are not locked. Yeah.
Are there any other questions? Yes.
On the conclusion slide, you had one bullet point was about possible Josephson junction or computational opticism. Singular, if this develops, what might it allow for
Oh,
computational?
I would say that's very speculative. I'm not sure what it will allow.
Any other? Okay, if not, thank you very much.